Good afternoon, everybody. Welcome to an exciting afternoon. I hope it will be exciting. Afternoon of Organic Chemistry, Chem 170, with your host, me, Dr. White. And I'd like to thank all of you for making me a YouTube star. And hopefully you're finding those videos are helpful, which is why I post them. All right. One of your colleagues was nice enough to remind me earlier today about something I should have mentioned on Wednesday, and I'll mention now. And that is, let's go look at the lab. This is the melting point lab, excuse me. And it says identity of unknown organic compound. That identity, it's one of these four compounds, only one. And in real life, when you do a melting point, you people especially, and that's where I got, your melting points are going to be just a little bit lower than these in the table, which we call literature values. I would probably hit it very close, but I've done a couple more than you have, like a couple hundred, couple thousand, a lot more. All right, so remember, this unknown, which you have to identify, which if we were face-to-face, you would too, you'd get the data on your own, but since we're not face-to-face, I gave it to you. It comes from table 1. These are the only four compounds that one of those is the identity of sample A. All right, any questions there? All right, couple announcements. I sent out on the 6th, as I promised, test number 1, because we had a delayed start. Instead of being this Wednesday, I postponed it by 1 week, and that's for your benefit. I could have pushed today and gone through it and finished everything. That's not right. You're not going to learn and do well on your test, and I want you to. So test number 1 will be on Wednesday, on the 16th, a week from this Wednesday. What do I mean by on that? I'll talk more about, well, I might as well talk about it real quick now. All right, the way I do test in this course online is usually sometime Tuesday before tests, which are all on Wednesday except the final, I will put in the assignment area a password protected PDF file for the test, in this case, test number 1. And then right after class on next Wednesday, we'll have regular class and lab. I will email you, each of you, the password for test number 1. You get to download it, or if you've already downloaded it, open it up, take about an hour or so. I'm not going to be there with a stopwatch because you're at home, but I will know if you're cheating, looking at your notes, because I put things in there and I catch people. Please don't. And you'll have until 10 a.m. the next morning to take test number 1, convert your answers into a PDF file, and then upload it. Just like with the labs, I'll have 2 files, 1 PDF, 1 Word, how to use Cam Scammer if you don't have a scanner, to use your cell phone, take pictures and make it into a PDF file, which you can upload. And I also have 2 files, Word and PDF, how to upload things to D2L, almost at Blackboard. That's the other school. And that's how we'll do it. So you have plenty of time to do test number 1, 2, whatever test you're taking. And I do the same thing with the final. And that's how we'll do testing here. Now, since I can't print it and then give it back to you, what I will do before the following Monday after the test is that 1, I will post your score, test score in D2L for you to see. And then for each person, I will send out an individual email with how many points you got for each problem. And then always the next class, which is why I give it on Wednesday, I will go through on Monday all the answers. However, since I don't want answers in my test floating around the internet for all time, I cut that out of the video. If you can't make it to class, always feel free to come to my office hour or schedule a special time, and I'll be more than happy to go with any answer on the test. And also why you missed points. Speaking about test number 1, this morning I posted test number 1. You also received this as an email, test number 1 information. And again, it's going to be on Wednesday, the 16th of this month. Test number 1 has 10 pages. I use large font, so don't be scared. And it has 14 problems. Some of the problems are multiple part, like part A, B, C, and D, just like I've done. Give the IUPAC name for this, give the IUPAC name for that, or other things. And I will never and never have given a multiple choice question on a test in this class. Never have, never will. Now we'll cover alkanes, that includes cycloalkanes, alkenes, alkynes, and aromatic compounds, which I will start today. Now, points breakdown. 13 points, general knowledge. What would be a good general knowledge question? Oh, I know. How many bonds to carbon? That's general knowledge. Hopefully all said 4. Then nomenclature. There are 2 types of nomenclature questions. One is, here's the compound, give the IUPAC name. The other is, here's the name, draw the compound. And finally, 47 points are reactions. All but one problem on test number 1 will be give the organic product or products for the following. One will be give all the products, I think, but most of them will be give the organic product or products, just like we have done in the problem sets and also in class. And it adds up to, oh, look, 105. And what does that mean? There's 5, yes, 5 bonus points. And why do I call them bonus points? That's because when I calculated the total number of points I used to get your percentage or divide into your points to get a percentage, I used just 100. But there's 105 you can get on there. There's 5, yes, 5 bonus points. Now, I don't do what some instructors do, which is make the last problem, the bonus problem, make it impossible. No, I just have the test add up to 105, and you pick, and you don't really pick, but you can consider any questions, the bonus questions, which is really, if you want to do it that way, I just have it, the whole thing add up to 105. And that's test number 1. Any questions about test number 1? And remember, I haven't said this in a while, but I think you guys are getting the hang of it. There's no such thing as a dumb question. All right, a couple other things. One, on Wednesday, I will go through the alkenes and alkynes problem set, double bonds and triple bonds on Wednesday. And also on Wednesday, at the beginning of class, and I'll be cutting this out of the video because I don't want it floating around the internet forever either, because someday I may sell it. I will, free of charge, actually have to pay to be in my class. So it's not totally free, but no additional cost. I will teach my method how to eliminate test anxiety, and it works quite well. All right, with that, it's time to get on with, well, let me just close a few things. And it's new chapter time. And let's talk about aromatic compounds. I think I might have mentioned some of this last week, but it's good to go back and review. All right, aromatic compounds are named that aromatic because they originally were originally the only organic compounds isolated from spices and herbs. And if you're a fan of history, which Dr. White is, for many, many decades, major European powers fought wars over aromatic compounds, spices and herbs. And that's why Columbus found America. He was trying to find a shorter route to India. Obviously, he didn't find that, but he found America. Or if you believe the Vikings were here first, they were here first, but he came over for that. And one of my favorite aromatic compounds is vanillin, which is found in vanilla extract. Ooh, do I have time? I do. Everybody see on their screen, Madagascar double strength vanilla extract? Thumbs up, people. Give me a thumbs up if you see it. Thank you. This is from the Spice House. There's one in Evanston, another in Chicago. I no longer drive to Evanston, the pandemic, so it's about an hour round trip each way from 2 hour round trip from my house, and I just have them ship it out. This is the best vanilla extract you've ever had. It's double strength, and yes, it's super expensive. It's worth every drop of it. Dr. White's a vanilla extract freak. I love it. I'll even put some of that in water with a little sugar. It's non-carbonated cream soda. This stuff is phenomenal. And it contains vanillin. And they come from the vanilla beans right there. And actually, when you buy a bottle, there's a bean or in the bottle itself. I think that's some marketing thing. Now, one thing about aromatic compounds, they have been found to have unusual chemical properties, especially their stability. They don't change with time. Some things go bad, you know, how butter, things like that go rancid. I'll talk more about that. And many have a ring that should actually be C6H5. And it is now. And this, I'll never ask you what's on this slide. Now, one other thing I should mention that by the end of the semester, you might want to look at. This is a great book. It's about time for me to read it again. Every couple of years, good books I like to go back and read. It's like going back and visiting old friends. And it's called Napoleon's Buttons, How 17 Molecules Changed History. And some of them are aromatic. Most of those 17 are organic. Now, why is it called Napoleon's Buttons? Because there's a tale. I don't know if it's true or not, and the authors really don't. Why did Napoleon's army lose in Russia? They say because of the cold, but one story goes is the buttons were made of very inferior metal, and the super cold of Russian winter, they became, and this is a chemical term, or actually industrial term, friable. They crumbled and fell apart. Well, if your pants and your coat, you can't keep them closed, or up because your buttons just disintegrated, you're going to have a hard time fighting in a war. And that's why they named it Napoleon's Buttons. But it's a fabulous book. After the semester, you should read it because you'll learn organic chemistry to understand it. All right, now when we talk about aromatic compounds, one of the greatest of all organic chemists, Kekula, comes to mind. And for many years, what's the structure of benzene? Benzene is the simplest aromatic compound, has a structure 6 carbons and 6 hydrogens. Now, if I were to draw a cyclohexane, notice it has 6 times 2, 12 hydrogens. Cyclohexane, which is not benzene, so the question was, what's the structure of benzene? And like I said, Kekula is considered one of the greatest of all organic chemists. And he was the first, or not the first, well, yeah, I guess the first to propose a reasonable and turned out to be correct structure of benzene. Now, if you're talking to an organic chemist like myself, and you say the word Kekula, immediately, if you know your organic chemistry, you should think about his snake dream. His snake dream? Well, when he got older in life, he was at a symposium, so the story goes, and someone asked him, how'd you come up with the name or the idea or the concept for benzene? And he said, the night before, I had a dream, and this big snake was chasing its tail in a circle and grabbed on and held on to its tail and was going in a circle. And that gave me the idea for benzene. And that's Kekula's snake dream. Now, that alone is a lifetime achievement, but he went on to do a few other things that might be important. He was the first one to recognize that carbon should have 4 bonds to it. That's called tetravalence of carbon. But we now take it for granted. Back then, it wasn't. He was the first one to, and I'm not going to ever ask you anything on the slide on the test, he was the first one to recognize that carbon atoms can be connected together by chemical bonds. And he developed that benzene contains 3 conjugated double bonds. Conjugated means alternating single, double, and so on. Now, is this cool or is this cool? Notice he lived from 1829 to 1896. I think by 1840 is when he came up with his concept for benzene. And here's the strut of his structures. It's called a Kekula structure for benzene. And notice there are 3 double bonds, and it's alternating double, single, double, single, double, single. Up until a couple of years ago, I was telling students, if you see this for sale, let me know. I'd like to buy one. About almost 3 years ago, students said, look here on eBay, they're selling them. I was surprised how cheap they were. I bought 2. They're only about a couple dollars each. Now, this is from a country that no longer exists, DDR, otherwise known as Deutsches Democratic Republika, otherwise known as East Germany, no longer exists. It's all one country now. But this was a stamp that they issued 25, I don't know if it's probably 25 Pfennig, which is their penny stamp. I've got 2 of them downstairs, frame in my living room with other chemical stuff too, mementos. Now, what Kekula came up with was the idea of resonance and the resonance model for benzene. Kekula's structure, and I'm going to show you benzene in a little while, for benzene differ only in the electron arrangements. Now, This first one, I used to, back here, I put brackets. You don't need the brackets. You don't need this anymore. If I say benzene, and it's got 3 double bonds, double, single, double, single. Why can't you put 2 and a double together? Well, geometry won't let you. And they're all cis. Now, if I were to take and move electrons, these over here, then I'd have to move these here to pi electrons and these here. And we have what's called a double-headed arrow, like I have a pretty one there. And the new structure would be this way. And if you move the electrons, which is what these arrows show, you can go back and forth. And this is what Kenneth came up with, his idea for benzene, which helps. Now, the double-headed arrow is resonance. You're only moving electrons, and it does not indicate a chemical reaction. And a lot of times in the past, and we don't do it anymore, you'd put brackets to indicate the structures can't be isolated. They both exist at the same time. It's like going back and forth super quick. Actually not. This is more a mnemonic device, a memory way, or not memory, a mind way of chemists being able to wrap their head around what's happening with benzene and aromatic compounds. All right. Click. The next slide or two, will it be on test? No, but it'll help you understand aromatic compounds, which is why I'm going to talk about it. All right. Now, the p orbitals, that's for one electrons, or the electrons for the p orbital, for the pi bond, also known, they form the pi bond orbitals to create a ring. And again, I'll show you a picture to make this more sense. And this is sort of a cloud of electrons above and below the plane of the benzene ring. And the benzene ring, unlike cyclohexane, is flat like a piece of paper, very rigid. Now, on this side, again, switches off. Each of these blue looks like an hourglass. That's called the orbital, where an electron is in each carbon. And how do you form a pi bond? By sharing electrons. So this could share, this could share, this could share, or this could share, this could share, and this. In reality, they're all holding hands, sharing electrons. How many of you have ever seen Ring Around the Rosie or played it? Or you grab hands and go around in a circle, Ring Around the Rosie, never mind. But anyways, I just had a memory that I want to bring back. I worked at one place one summer, grounds maintenance, and part of it was Hadley School of Blind. And it was touching but sad seeing blind children play Red Rover. But anyways, they were having fun though. This, if you look from the top here, it looked like a donut. Now, switches off for this slide, but some entrance exams ask this question. I will never put it on my test or final. When you have a cyclic compound, how do you know if they're aromatic? This formula, 2n plus 2 equals the number of pi electrons that are conjugated. And n is a whole number. And if I draw one resonance form of benzene, ooh, Dr. White's having a good ring drawing day, look out. You'll see each double bond has 2 pi electrons, a pi bond has 2 electrons, and 2 plus 2 plus 2 equals 6. When n equals 2, this is true, so this is aromatic. But I will never ask that on tests, but I've been told some entrance exams for certain types of professions will ask that stupid question. All right, now, there are different ways of drawing benzene. One is the calculus structure, and the other is the delocalized polycloud. I think the calculus structure looks cool beyond cool, so that's the way I always write it. But you can do the circle in the center to show like the pi electrons or the pi cloud when you're looking down, like here. If your eye was right here and you're looking down, you'd see a circle. All right, switch is on, click. All right, nomenclature of aromatic compounds. Now, it turns out chemists have been investigating benzene for eons, and that's a common name. And IUPAC, in their infinite wisdom, in certain common names that have been so widely used, they just said, all right, we're going to make it the IUPAC name. And benzene is one of them. Here's the structure of benzene. You should know that. Oops, I didn't want to close that. Sorry about that. The joys of Zoom. All right. Now, if all right, benzene is a six-membered ring, and it has three conjugated double bonds. 1, 2, 3. This is benzene. Now, there's another, what's called resonance form. Usually this is the one I draw. Don't ask me why. I could just easily draw this one. And that's also benzene. Now, if you wanted to use the delocalized pi cloud, the first two are called calcula. That's benzene. Now, common mistake on test one is if somebody's drawing a benzene ring and they do that, and I mark it wrong because this is cyclohexane. And these are as different from this one as your foot and hand are, or as night and day. The three here, these are benzene. And this one obviously is not. You have to put something inside one of these three structures like that. And it's a common mistake. I had one student a couple of years ago because she forgot to do this on reactions and put anything in there. It was cyclohexane, and she lost 12 points. Oh, was she upset? I would be too. Which is why I'm warning you, make sure you put in the double bonds, either this structure or this one, or the circle for the delocalized pi bonds. I like, and you'll see me usually this one, I rarely do this one. I almost never, ever do that. That's just my personal preference. Any three of those would be correct on the test. And that's the structure of benzene. And a common mistake, students, if I ask, give the name of that compound, it's benzene. Students will put cyclohexatriene, tri-3, ENE double bonds. Wrong. It's called benzene. Now, what happens when you put a methyl group on benzene? Is it methylbenzene? No. That compound also has been around for eons, and we call it toluene. And you should know toluene is a benzene ring. Here's the way I normally, these are resonance structures with a methyl group on it, and it can be on any carbon. If you were to draw, if I asked you to draw the structure of toluene, and you do this, I'll mark it wrong because that's methyl cyclohexane. You have to put the stuff. Now, another way of drawing toluene, which this is about the last time I'll do this, is what is called the delocalized pi bonds circle inside structure. That's toluene. Now, sad story. Now, this is sad. How many of you have ever heard about, read about people who sniff glue? And in the old days, it would rot out your brain and other organs in your body, and eventually it'd kill you. What were they sniffing? Benzene or toluene. For many years, airplane glue for model airplane builders had toluene in it. And if you sniffed it, guess what? I guess they got some sort of high out of it. Don't do that, please. It'll destroy your body. And if we go and look at the MSDS sheet, does everybody see material? Is everybody familiar with the material safety data sheet? Every chemical that's sold in the United States, every chemical that's made in the United States has an MSDS sheet, material safety data sheet. Go to your favorite search engine. Mine is Google. Put in the name of a compound and then the letters MSDS. And notice right at the front, emergency overview, target flammable, causes skin eye and respiratory irritation. And the dizziness is probably what people have thought of, and can enter the lungs and cause damage, possible risk to harm to unborn children, may cause central nervous system depression, may cause liver and kidney damage. In other words, it will do you serious harm. And MSDS sheets are standardized. Section 1 is its name. Composition is 100%. Emergency hazard identification, different ways of first aid, fire, and so on. And here, OSHA has only 200 ppm limit that you can inhale in an 8-hour period, and the total ceiling, which is quite low, 300 ppm. This stuff is dangerous. How dangerous? Back when I was very young, a cousin of my mother's had been a painter. And back in the 30s, 40s, and 50s, paint wasn't made with latex. It was made with an organic solvent and pigments. And there are a lot of fumes painters inhale. And a lot of those paints were made with benzene or toluene. And this cousin had been a painter all his life. And by the time I met him, he was in his early 60s. And he was just about a couple inches above being a vegetable. I mean, I don't know if I'm saying this properly. I'm not a medical doctor, but his brain was not much was working there. It was very sad. And luckily, we now know better. And as you saw in the MSDS sheet. So you should know this is the structure of benzene. Other ways of drawing it would be this other resonance form or the delocalized pi. And this is the structure of toluene. This over here with the X is methyl cyclohexane. Now, you should know those. Now, this structure is called styrene. I'm not asking you to learn this one, but I thought I'd put it down. When you have this called a vinyl group on a benzene ring, we call that, again, the common name, which became the IUPAC name, styrene. Poly means many. You put a lot of these together and bond them together, we have polystyrene. Anybody ever hear of that? You know, the white insulated cups or the very cheap white insulated like foam bead coolers you can buy dirt cheap. I don't know what the price of dirt is, but it's not a lot. It's made from this compound. That's why they call it polystyrene, because it's made from styrene. Now, when you have two or more groups on a benzene ring, you can use numbers, but most people don't use numbers. There's another way, which I'm going to ask you to learn, and that's special name used instead of numbers when you only have two groups on there. And right now, I would like to write something on the whiteboard, if I get it up. Oops. There we go. All right. The first one that's got a benzene ring, here's an ethyl, here's an N-propyl. Second one has the same thing. And the third one has an ethyl group and an N-propyl, which I forgot to put the rest of it. Now I did. Now these are not identical because the different substituents are on the ring in different locations. I call this one, this is 2. I call this one, this is 1, 3. If I call this 1, 2, 3, 4. So this is 1, 2 disubstituted. This is 1, 3 disubstituted. And this is 1, 4. And organic chemists, I don't know how, one day I looked for it and I couldn't find it, came up and have been using this for eons. And for what's 1, 2, and let me erase this and write it better. Ortho. So this is ortho, ethyl, and propylbenzene. Notice it's 1, 2 disubstituted. 1, 3 disubstituted. Notice 1 and 3. That's called meta. So this would be meta, ethyl, and propylbenzene. And 1, 4 is called pure. And if we were typing these, those would all be lowercase, but since I'm handwriting, I do both. I don't worry about it. And there should be no space, but anyways, I'm going to have some space there sometimes. So 1, 2 disubstituted, ortho. Therefore, this is ortho, ethyl, and propylbenzene. 1, 3 disubstituted, meta. Therefore, the second compound is meta, ethyl, and propylbenzene. And finally, the last one, 1, 4. You pick one of those and count 1, go clockwise or counterclockwise to get the smaller number to get to the other group. And that is 1, 4. Therefore, that's pure, ethyl, and propylbenzene. And again, ortho 1, 2 disubstituted, meta 1, 3, para 1, 4. One of these decades, I'll do a table actually in the lecture, but I never have. I usually write it on the board like I just did. And you should know this. If you put a number down, 1, 2, I'm going to mark it wrong because I'd like you to learn ortho, meta, and para. Now, any of you ever hear of the ortho chemical company or pharmaceutical company? Anyone? Well, it exists. It's a major pharmaceutical company. I wonder where they got their name from. Ortho. Even though I don't know if they're compounds. Let's do something real quick. That's not what I wanted. And it's now a subsidiary of J&J, but for a long time, it was its own standalone company. When was it bought? Doesn't say here, but anyways, I wonder where they got their name. Well, you know now. Now, this is a special name used instead of numbers for only 2 groups on a benzene ring, aromatic compounds. It's never been used in cyclohexane, so don't. I'll mark it wrong. I don't know why someone came up with this, but they did, and organic chemists use it. Now, before I do some examples, I held off until now but there are certain substituents besides methyl, ethyl, N-propyl, isopropyl, N-butyl, and tertiary T-butyl, I would like you now to learn. When you have a chlorine on a ring or benzene ring or cyclohexane, it's called a chloro group. When you have Br bromine on a ring like benzene or other things, it's called a bromo group. When you have an iodine on a ring or other things, it's called an iodo group. And when you have fluorine, you have fluoro. Now, there's a very important group, NO2. And the bond to the, like a benzene ring, goes to the nitrogen, and then these oxygens are bonded to the nitrogen. And that's called the nitro group. Now, these I expect you to know. Another one, which we'll talk more about later in the semester, is when you have SO3H, the bond to the ring, like a benzene, goes to the sulfur. These oxygens are on the sulfur, and this hydrogen is on one of the oxygens. And that's called the sulfonic group, or sometimes called sulfonic acid group. And that is used to make the molecules in your laundry detergent, among other things. I don't know about you, if you like clean clothing, I like laundry detergent. And that's what I did this weekend. I caught up on a lot of laundry, different colors and stuff and everything, got a lot done. But, and on a benzene ring, the alkyl groups are methyl, ethyl, just like you've already learned. So let's go through this again. Cl chloro group, Br bromo. I don't think I have a file for this. One of these days I have to. Iodine, iodo, fluorine, fluoro. I always get the U and O mixed up. So if you misspell it on a test, I don't take all points, because I do it once in a while. Nitro, NO2. And those you should know. And the sulfonic, I'll never put on a test, but I'll talk about it later on, especially when we get into detergents, and also an important reaction I'll talk about in this chapter. And alkyl groups you already know. So let's do a quick example first. This is almost break time. First of all, whoops, wrong color. And what's the IUPAC name for this? Well, oh, look, what do we have? 6-membered ring, 3 alternating double bond. That's a benzene ring. And next, I have Cl chlorine. And that's a chloro group. Now, when you have one substituent on any ring, you never use a number. So I'm done. That's chlorobenzene. Oh, let's do one more real quick. And NO2 is a nitro group, and I'll let you try this one. What, excuse me, what would be the IUPAC name for the following? Remember, NO2 is nitro. All right, since it's almost time for the break, I'm going to do it. NO2 is a nitro group. This is a benzene ring, so this would be nitro, benzene. Since there's only one substituent on the ring, no number. And with that, it's time to take a break. Oh, I went a whole minute over. Come back at 1:56, and I'm going to get up and stretch. And I'll see you in 5 minutes. time to get going. All right, we're talking about nomenclature of aromatic compounds, really benzene and toluene. There are others, but I'm going to stick to that. And I was talking about how there's special names for them when you have disubstituted. And 1,2 disubstitute is ortho, 1,3 is meta, 1,4 is para. And I also showed you new substituents, and that's Cl is chloro, Br is bromo, I is iodo, F is fluoro, NO2 is nitro. Now, the sulfonic, I'll never ask in a test or a final, but I will talk about it in class. So it's good to know that group. And the alkyl groups you already know. So let's go back and practice this. Now, if we look at this molecule, notice we have a benzene ring. So the root name is benzene. Has a chlorine and a bromine. And I'll accept two different orders. Correct is bromo, chloro, benzene. But where are they? If I say this bromine is on 1, the chlorine is on 2. And 1,2 disubstitute, let me put up the chart. And 1,2 is ortho, 1,3 is meta, and 1,4 is para. So this is 1,2. This would be ortho, bromo, chloro, benzene. And I'll let you try this one on your own, because I'm going to share the fun. What would be the IUPAC name for that molecule? And I think everybody's done. So let's take a look at this. We have a bromine and a chlorine, and it's 1,4. This would be 1, 2, 3, 4. 1,4 disubstitute is para, and a benzene ring. And this would be para. Now, when it comes to toluene, something interesting happened. And that is, let's look at the following. Now, we have toluene, that's the benzene ring with the methyl group on it. That's the base name. It's not methylbenzene, common mistake. And iodine is iodo. Now, someone decided, even though toluene includes the methyl group in the benzene ring, for nomenclature, let's still consider that methyl group a substituent. And notice it's 1, 2, 3, 1, 3 disubstitute. There are two things on the benzene ring, even though it's called toluene. 1, 3 is meta. So that would be meta-iodo-toluene. And that's just the way it is. And why don't you try this one? Remember, Cl is chlorine. What would be the IUPAC name for that molecule? Remember, a methyl group on a benzene ring is called toluene. And also, I haven't said it today, but it's still true. There's no such thing as a dumb question in my class or in my world. If you have any questions, always feel free to ask in class, after class, or don't forget tonight from 5 to 6:15, I'll have my office hour. And last Wednesday, I had a couple of visitors, your colleagues. I was able to help them out, which is a good thing. All right, let's get going. What do we have? We have a methyl group on a benzene ring. The 3 double bonds, the lines inside tell you that's a benzene ring. We call that toluene. Cl is a chloro. Oh, look, somebody put a nice little table up here. And 1, 4 is para. And that would be parachlorotoluene. Now, next one, you don't have to write down, but I thought I'd show you an interesting one. I wish everybody had their monitor on, but you don't. Everybody see what I just wrote on the board, whiteboard right here? Anybody think of what that is? Time's up. It's paramedic. Para 1, 4, med, ic. You can all groan now. That's paramedic. Oh, last summer I had a paramedic in my class. He thought he went and showed the whole fire station that. He didn't get it, but he loved it. But anyways, all right. Now let's do a couple more. Remember, 2 is di, 3 is tri. And why don't you do the IUPAC name for the following molecule? And I don't have it here, so I'll write it up. we were in class on one part of the board. I wouldn't erase, and you can see. All right, I think everybody's done. So let's take a look. Oh, look, we have a benzene ring. So the root name is benzene, not cyclohexene or cyclohexane or cyclohexatriene. That's a common mistake on test 2. I'm telling you that. And look, we have Cl as chloro. Ooh, I've got 2 of them. And now notice they're 1,2 disubstituted, and that means they're ortho. So it's ortho dichlorobenzene. All right, now, as I mentioned earlier, on test 1, there'll be, I think, 45 points nomenclature. Why? Because we spent a lot of time just going over the basic nomenclature rules. What's 1 carbon chain, methane, 5 pentane, and so on. Then I taught you how to number with substituents and all that. And that's why I have a lot of, after this chapter, we'll be spending more time on reactions and less on nomenclature, but we still will go over nomenclature. And someday soon, if you see on something I sent you, it says 3 points each, draw the structure for. And the question is, draw the structure for benzene. I'm going to let you try this one first, then I'll do it. It'll be tough on you. Not really. All right, I think everybody's done. And you could have drawn this. You could have drawn this, which is called another resonance form. Or you could have, which I rarely do, except for this first day, you could have done this. Either one of these would be correct. If you did this, this is not benzene, it's cyclohexane. And I'd mark it wrong. So make sure you do that. And why don't you try this one? And that would be meta-iodo-nitrobenzene. Iodo is I, and NO2 is nitro. And in case you haven't memorized it yet, All right, I think everybody's done. I better get to work. All right, how do you decode the name when it's more than one word? You start from the right and move left. If I look at that, I say, oh, benzene ring, and I learned how to draw it there. I'll draw one of these resonance. If you use circle, that's fine. I have a nitro and iota, and meta is 1,3 disubstituted. Now, you could have written this as 1, 2, 3, or you could have written this and there are other ways you could have written it. One carbon of the benzene ring has an iodine, and going clockwise or counterclockwise, 3, you have a nitro group. And remember, molecules rotate, so there are many other ways I could write this. In fact, the real quick one here's another one. There are more. So luckily, you have an instructor as a piece of paper signed by the Board of Regents of Michigan State University, my PhD degree, that I understand those are all correct. Oh, this is fun. Let's do another one. And why don't you draw the structure of parachlorotoluene? And Cl chloro group, chlorine molecule atom on a ring. Oh, excuse me. A yawn just slipped out. Remember, toluene, CH3, and a benzene ring. All right, I think everybody's done. Anybody need more time? All right, let's take a look at this. How do you know what to decode? You start from the right, move left. Toluene, benzene ring with a methyl group, CH3. Chloro, that's Cl. Para tells you it's 1, 4. This is 1, 2, 3. This is 4. Now, another way of writing it, if you wanted to, which would be perfectly correct. Now, I've done is inverted 180 degrees, and you could also rotate it. There are a whole bunch more you could write, and those would all be correct. Oh, let's do one more of these. And why don't you write the structure, draw the structure for orthonitrotoluene. And over on the right, since you've just learned it, you might not have forgotten it. If we're in a classroom, part of whiteboard on say we're in 140 at building M, would be on the left of the screen that you would be facing with this projection. And this would be on the right side of the board. But since Zoom doesn't let me do more than one share at a time, well, I make the best of it. All right, I think everybody's done. I'll give you another 15.8 seconds. I'm looking at my watch with the second hand. All right, let's do this. How do you decode orthonitrotoluene to know what to draw? You start here and go from your right to the left. Toluene, a benzene ring with a methyl group on it, and that's toluene. Don't forget the stuff in the ring, that or a circle. And nitro group is NO2, and ortho is 1,2 disubstituted. And this is one, you can go either way, clockwise or counterclockwise. Most are going to go clockwise. That would be one example. And this would be another one. There are many other ways. On the ring, there's a methyl and an NO2 nitro group, and they're 1,2, one next to each other. And that's how you do nomenclature for disubstituted aromatic compounds. Oh, let's do one more. And why don't you draw the structure for bromobenzene? Remember, bromo, Br, bromine group. Bromine, Br, bromo group for bromine. In case you don't know, this Wednesday is organic chemistry students taking Zoom. Turn on your webcam National Day. Nah, that didn't sound too convincing. All right, let's do it. How do you decode this? You start from the right, move left. Benzene. Don't forget the stuff in the ring. Bromo, Br. You could have also done this. Put it on any other carbon and I could do it a couple more. That looks better. Now, if you wrote this down, that's bromocyclohexane, and that's wrong because you forgot the bonds here or a circle inside. So make sure you put the stuff inside the ring. Now, when you have more than two groups on a ring, you use numbers. And let's look at an example of one. Now, if we look at this molecule, the question is, give the IUPAC name for it. Well, I've got a benzene ring, but I've got a methyl group on it, so the base name is toluene. Oh, look, NO2, a nitro group, two nitro groups, three nitro groups. Remember, two is di, tri is three. So this would be tri nitro toluene. Now I'm not done. Now for toluene like this is considered carbon 1. Therefore, this nitro group is on 2, 3. This would be 4, 5, 6. When you see tri, which means 3, you need 3 numbers. And therefore, this is 2, 4, 6 trinitrotoluene. 2, 4, 6 trinitrotoluene. 2, 4, 6 trinitrotoluene. That's hurting my jaw. And I tell you, organic chemists are lazy. Sometimes they abbreviate things. And this is the structure for TNT, the explosive, 2,4,6 trinitrotoluene. Now that's a liquid at room temperature, so I'm told. I've never made it and don't want to, because you can kill yourself real easy. Now it's time for Dr. White to tell you an interesting story. TNT trinitrotoluene. If I had a bottle of trinitrotoluene and had this much in there, and I slammed it down like that on my desktop, you would now have witnessed a large explosive. And I'd be gone. My house would be gone, which I will not do, because that's why I don't. Now, it turns out TNT is a very good explosive. Well, except how do you handle it? Back in the late 1800s, if you had a horse and wagon, you had a lot of explosions. Roads weren't that good. Well, it turned out 2 brothers came up and found a way to make it safe by mixing it with clay and other things. And then you could mold it into sticks, wrap paper around it, and use blasting caps to explode it. And the name of their product was, and still is, dynamite. And who came up with that? The Nobel brothers. Nobel, I've heard that name before, Nobel. How many of you ever heard of the Nobel Prize? I hope you all have. There's one for chemistry, medicine, physics. I want to say there's a Nobel Prize for literature, but I might be wrong on that. But anyways, there's one for peace. And how did the Nobel Prizes get started? Well, Alfred Nobel became very rich with their invention. A sad story, his brother was killed in an explosion in one of their plants. It was still dangerous dealing with TNT, even making dynamite. And whether it's because of his brother or other reasons, he's donated the money to send up a foundation that gives out the Nobel Prizes along with some money. Now, have you ever wondered where did Alfred Nobel get all his money? Well, it turns out making TNT safe for explosives was very, I don't know about now, but then very lucrative. And who are his biggest customers? The different militaries of the world back then, armies. And because they used his safer explosives for war. So think about that. The Nobel Prizes were funded mainly by money that came from military application of their invention. Is there anything wrong with that? No, but I just thought I'd show you that. And remember, this is trinitrotoluene, and it's abbreviation TNT, and it's got this structure, otherwise known as boom, explosive. Nitro groups decompose very quickly to give off oxygen. That's why it is. All right, let's try one for you. And there you go. What would be the IUPAC name for this molecule? 3 points each. Don't forget, on Wednesday, I will go through the alkenes and alkynes problem set. Also, near the end of the, I'll do it at the beginning. At the beginning of the class, I will teach you my method, how to eliminate test anxiety, but I'll cut it out of video. For those who can't make it to the lecture, see me during office hours, or if you need, I'll set up a special meeting and I'll teach you that. Again, give the IUPAC name for the following. And here we use numbers. Br is bromo, Cl is chlorine or chloro, and you should know the top one. All right, I think everybody's done, so I better get to work. And the question is, how do you name this? Well, I've got a benzene ring. I've got a T-butyl group. I'm not going to call it tertiary anymore, or tert-butyl, because everybody calls it T-butyl, a bromo group, and a chloro group. So this would be now, I'm not going to, oop, I said I wouldn't do this. Better keep my, there are different orders. Now, here I should have left my, this one I think I made a little too hard. I'll do the easy way. It'd be 1 T-butyl, 2 bromo, 3 chloro. And I didn't do it correctly, but technically it really should be 1 bromo, and it would get much more complex. Let's do another example. Once in a while, I'll do an example that's way too difficult, and I won't do that again. And why don't you try this one? This is pretty straightforward. On my tests, I don't try and do things that go into gray areas that I would have to think about and you would probably have problems with. That's not fair. And that's not how Dr. White operates. All right, I think everybody's done. Let's take a look at this. What do we have? Oh, we have a benzene ring with a methyl group, and that's toluene. I have not one, but I have two chloro groups. So that's dichloro. And let me erase these numbers so not to confuse you. The methyl group, by definition, is one. Therefore, you go in the direction, give the other alkyl groups or substituents, in this case, the lowest number. Whenever you see di, you need two numbers. So that would be 2,4-dichlorotoluene. All right, there are two types of questions. And the other one is, here's the name, draw the structure. Excuse me. Got a feather in my throat. I don't have any birds though. That's better. So how do you draw this? I'll do this one, then I'll share it. You start this way. On your right, move left. Benzene ring. Remember, don't forget to put the circle or double bonds. I didn't. Then chloro, that's Cl. Tri means 3. And it's on carbons 1, 2, and 4. So this is 1. This would be 2, 3, 4. And that's how you do it. Again, benzene ring, chloro, tri is 3, then 1, 2, 4. I'll call one of these 1, then go clockwise or counterclockwise, 2, 3, 4. And carbon 2 and 4 are my other chlorines. Yes.
Excuse me, Prof. I have a question to ask.
What?
I have a question to ask. So
Go for it.
toluene, like where we have the chlorine in first and third ring. So you don't use the prefix, the meta, the ortho, and the para. Don't you use that there?
Say that again. You put, we did the benzene ring. Then I know chloro-Cl.
No, the previous one before this one, the 2,4-dichlorotoluene.
All right.
So my concern is.
All right.
Yeah.
Toluene is this molecule.
Mm-hmm.
And when you're numbering it with other things and you're not using ortho, meta, and para, this is the number 1 position. So here I have toluene, and I wrote this. Now I have 2 chlorines, Cl, and they're on carbons 2 and 4. If this is 1, the one next to it is 2, then 3, then 4. Are you with me? And this one would get a chlorine, and this one would get a chlorine. Ooh, I got it right the second time too. Am I good or am I good? Does that help, Vivian?
Yeah, okay. My concern was, where since we have,
Okay.
okay, that's okay. That's fine.
Well, thank you for your question.
Thank you.
All questions are good questions in my world. And why don't you try this one? You draw the structure for the following. In case you don't remember, this is how you draw an iodine, which is an iodo group. I hope you all had a good week and weekend since we last met. I got a lot of work done this weekend around my house, a lot. Plus I did cooking. My training is as a batch organic chemist. I have a huge freezer that I keep stocked. I make a lot of something and I freeze it in individual portions because during the week I never cook. I grab some things, put it together and throw it in my microwave. I just don't like cleaning up during the week. Weekends, I'll cook a couple hours and fill my freezer, which is quite full. All right, let's do it. Start from the right, move left. Benzene, member, 6-membered ring, either circle or 3 conjugated double bonds. Conjugated means double, single, double, single, double, single. All right, iodo is iodine, tri means 3. And I can say this is 1. And then if this is 1, this is 2, this is 3. And that's how you do it. Oh, let's do one more. I'm having a good time. And remember, as one of your colleagues just said, oops, one of the bad habits Dr. White has me is I'll draw structures instead of names. I just like drawing structures. It's fun. And why don't you draw the structure of 3,4-dinitrotoluene. Remember, nitro is NO2 group. Oh, I don't know if I forgot to mention, last Thursday, I went to my eye surgeon, ophthalmologist, for a 8-week follow-up on my cataract surgery. Things are going great. And he did a vision test. Are you ready for this? I forgot what my vision was before the cataract surgery, but I wouldn't, as soon as I got up, I'd reach for my glasses Now my vision is 2025, almost perfect 2020. And that is so nice. All right. And if you know anybody who needs a good eye surgeon, feel free to contact me by email. Speaking about email, make sure when you're sending me an email, use kwhite@elgin.edu. If you look at the one I send out from Blackboard, it pops on a student ending because it's going through Blackboard. Don't use that because I'll never see it. All right, let's do this. How do we determine what to draw? Start from the right, move left. Toluene, six-membered ring, benzene ring, don't forget the bonds, with a methyl group. The toluene is carbon 1. I have nitro. Oh, look, somebody was nice enough to write NO2. Di means 2. And where are they? They're on carbons 3 and 4 of the ring. If this is 1, this is 2, this is 3, this is 4. So I have 2 nitro groups. And there we are. Now, on a test, you don't have to write the numbers, but I do, because I don't know if I told you, it helps to let the paper do your thinking. And I forgot when, but sometime later in college, when I figured that out, my test scores went up and they were good to begin with, got better. And throughout grad school, I always did that too. And I've taught students that. Oh my goodness. Time flies when you're having fun with aromatic compounds. Let's take a 5-minute break and we'll continue. Time to get started again. Now, next two slides, 3 slides, I'm going to turn the switch. Will this be on a test to the off position? Everybody see, click. And, oh, I don't know how this got an extra dot. There. Now, there's something called resonance energy of benzene. Now, it turns out, if you look at benzene, it's got 3 double bonds, but they're conjugated, alternating double, single, double, single, double, single. And that's benzene. And normally, you know, from the last chapter, take a double bond and boom, you break the pi bond and you add a hydrogen to each carbon double bond. Well, it turns out benzene, it's pretty hard to do that. I mean, real hard. And what do I mean by that? You have to heat it to very, very high temperature for a very, very long time. And eventually it will, but it's harder. And it does not react as if there were 3 separate double bonds. There's something, remember, switch is off right now, but it's just important to understand the reactions I'm going to show you for benzene. Something different in benzene, and actually in all aromatic compounds. Speaking about aromatic compounds, either I missed the slide or forgot to do it. Let me do something real quick. There's one. All right. Now, I'll teach you later about different functional groups, but this is the structure of vanillin that is responsible for the good taste of vanilla extract. And notice right in the middle here, you don't have to write this down, is a benzene ring. It's an aromatic compound. Now, there's some really interesting stuff I'll teach you about later on, but this is an aromatic compound. Now, if you look on your screen here, this is the molecule called cinnamaldehyde. I wonder what it tastes like. This molecule is responsible for the taste of, smell of cinnamon. Now, I love cinnamon. My older sister hates it with a passion. Well, what can you say? But I like cinnamon. And notice here you have a benzene ring. And that gives this, it's an aromatic compound. It's also got a double bond. And this is another functional group I'll teach you about. It's called an aldehyde. But this is a molecule, an aromatic compound that gives cinnamon its characteristic smell and taste. And the molecule you now see on your screen, the upper right, is called raspberry ketone. I don't know about you, but Dr. White loves raspberries and also other berries too. And this molecule also has a benzene ring in it, has other stuff I'll teach you about later in the semester, and it's responsible for giving raspberry its odor and taste. And it's an aromatic compound. And these are all very stable. And they don't react that easily. So something's different about benzene and all aromatic compounds. What's that difference? It's called stabilization, or as I like to call it, resonance energy. And this is the difference between the energy of a real molecule and the calculated energy of the most stable contributing structures. Now, if we look at benzene, and you wanted to calculate it, you'd say it has 3 double bonds and 1 ring. And from this, you'd get what's the energy calculated for that molecule. But in reality, real benzene, I don't know if this is their false benzene, when you go in the lab and measure the energy, it's much lower, which means it's more stable. The lower the energy of a molecule, the more stable it is. The more stable, the less likely it wants to react. And aromatic compounds are more stable than non-aromatic compounds. And this is due to what we call resonance energy, difference from what is to what is calculated. And the reason for that resonance stability, hopefully nobody's getting, are these p orbital electrons forming the pi cloud or pi bonds, and they're all holding hands like in a circle. And that makes us very stable. And if you break one into double bonds like right here, you lose all that stability of them holding hands. And they don't like to do that. Notice how I'm giving atoms an ability to think and have feelings. They don't, but it's good to think that way. So what does this resonance energy mean? You're not going to do chemistry normally with the double bonds in a benzene ring or toluene. But what you can do is, ta-da, electrophilic aromatic substitution. Wow, those are some big names. What does that mean? Well, substitution means you replace one thing for another. Substitute it. Aromatic, we're talking about an aromatic ring. But what's that word electrophile mean? What is the word electrophile? Ooh, electro comes from electron, and that has something that has a negative charge to it. And where do you find electrons real easy in a benzene ring? Aromatic compounds, the pi bonds. The pi bonds, each pi bond is 2 electrons. We've got 3 pi bonds, and you saw those clouds, and those are full of electrons. Now, phile, what does that mean? Anybody ever hear of an audiophile? That's someone who loves audio music. Phile is Greek for lover. So an audiophile is a music lover. And by the way, I have, let me think, 1, 2, 3, 4, 5 stereos in my house. My big one in my family room, well, I don't talk about that because it's expensive. And the others are quite good too. I even got a stereo in my garage, so when I'm working in there, I can listen to music. And I'm an audiophile, but electrophile is something that loves electrons. So electrophilic aromatic substitution is some group that's looking for electrons, sees the aromatic ring, and substitutes one of the hydrogens for something else. And why does this happen? Because due to resonance stabilization, resonance energy, aromatic compounds do not undergo addition reactions to the double bond easily. They undergo substitution. And these are chemical reactions where the hydrogen atom on the aromatic carbons of the benzene ring or other aromatic compounds is substituted with another atom or group of atoms. Now, normally on a ring, you don't show hydrogens, but remember, each one of these carbons in the ring has a hydrogen. And that's why benzene is C6H6. Oops, H6. And what happens is in the reactions of benzene and other aromatic compounds, you replace one of the hydrogens with something else. And that's electrophilic aromatic substitution. All right, let's look at our first electrophilic aromatic substitution reactions. And that's called halogenation. Now, unlike a double bond, even this is still not that reactive, so you need a catalyst, ferric tribromide or trihalide, along with halogen gas. Now, in real life, this is only done mainly for chlorine or bromine. And if you take a benzene ring and react it with halogen gas and ferric trihalide, you'll replace one of the hydrogens here with a halogen. Now notice you'll also make HX, which is an acid. This is inorganic. And organic chemists are very biased and say, I don't have to worry about that. And on my test, I'll ask you the organic product or product. If you want to write down whatever HX is, feel free to do that. If you don't, I don't care. I'm not going to look for it. Now, some students like to write all the products. Organic chemists are lazy. We're just interested in do we make the organic product or products we're trying to make. So let's take a look at this reaction. Now, let me remind you, this is one way to write a reaction. Organic chemists can also write it this way. A plus B reacts with B and C to make D. And the other way, which we write a lot of times, is don't ask me who started it, but I've learned it that way, and I do it that way, like other organic chemists. And what this tells you is benzene react with bromine and ferric trihalide catalyst, and the general reaction don't forget to put the double bonds or circle. And for this, in real life, these are the only two halogens used. And therefore, what's X? In this case, bromine. I still have my benzene ring. Don't forget the double bonds inside 3 of them. And I make bromobenzene. And now it's time for you to have some fun. Oop. And it's your turn. What's the organic product or product for the following reaction? 3 points each. And don't forget, time for a commercial from Dr. White. Tonight, I'll have my office hour from 5 to 6:15. Second, don't forget the lab we did last week is due this Wednesday. Also, you should be uploading the signature sheet to D2L also. If you don't have a printer, just put down your data and the question number and the answer to the question, and use CAM scanner, if you have a scanner, that too, to upload a PDF file. Or if you want, you can also use the Word doc. All right, I think everybody's done. What do we have here? A benzene ring. What are we reacting with? Halogen, chlorine, and ferric trihalide. Remember here, X can be chlorine or bromine. And what happens? You do not break the double bonds. It's a common mistake students make. You don't. You replace one of the hydrogens with a halogen. What's X? Chlorine. It doesn't matter which carbon you put it on. Mostly you're going to put it on the top, and you make chlorobenzene. And that's how you do it. Now, I need to talk about something important, the way I designed this class. If you remember the first day of class, I asked, how many of you are planning on an enriching career in organic chemistry? And none of you raised your hands, and that's fine. How many of you are planning on getting a PhD in chemistry? I did, but nobody else did. So I know you're not going to become organic chemists, and most of you are in health-related fields. So what does that mean? I'd rather spend later in the semester more time on things that are important to you, like fats and oils, carbohydrates and proteins, and other things too, as opposed to the following. And therefore, I'm just going to mention it, but in this class, I will never put it on a test. We'll have a lab where it'll allow you to learn a little about it, but let's look at the following. What if you did this reaction with toluene? You could have a lot of other things. And let's say we use chlorine. And we know the general reaction is you replace one of the hydrogens with a halogen. Well, let's take a look at this. When you had nothing on the ring, like here, it doesn't matter where you put the chlorine. What happens, by the way, this stuff I'm doing now right here switches off, and you don't have to kind of write this down. Now, if the chlorine coming in, where can it go? It can go here, and this side is the same thing, and that would be the ortho position. It can go here or here, and that would be the meta position. Or it could go here, and that would be the para. So where does it go? Well, it turns out what substituent, in this case, the methyl, is already on the ring, dictates that. Now, I'm not going to be teaching this because You could spend the next week or so learning this and finally get it down, maybe a week and a half. I'd rather spend that on more things that are more germane to your daily life and your future life, because after this class, none of you are ever going to do electrophilic aromatic substitution. What's the important reaction? Now, it turns out the group on the ring, in this case methyl, is called the director. And a director, have you ever gone to one of those concerts or fairs and they take an open field and make it into a parking lot? Or even some big ones where they have a parking lot, and you got those people say, no, don't park here. You want you to fill up this row first. They don't like me because I don't listen to them. And I don't like them because I don't like being yelled at. So I don't go to those anymore. But they're directing you where to go. Well, it turns out the group on there is a director. And if it's electron withdrawing, which means it's liking to suck some electrons out of the ring, or if it donates electrons to the ring, electron donating, that dictates where does the incoming group go. And there are two types of directors. Again, switches totally off right now. I mean, big time off. And I'll be teaching you again when we do a lab with this. And one type is ortho-para. I should spell it out. And again, you don't have to copy this down. That means if something's coming in, you have an ortho-para director, you'll get product on the ortho and the para. The other type is a meta. And that means you'll get it here or here, the same thing, meta. And that's important. However, for this class, I'm not going to teach that on the test or the final. So what does that mean? These are the only two problems I can put on a test for halogenation of a benzene ring, because I'm not going to put a director on there. I don't want to waste valuable time this semester on teaching you directors for a lecture or a test, as opposed to teaching other stuff, which I think is more important, and I do. So these are the only two examples. I'm done. It's time to move on. Uh-oh. Yep, it's time for me to close up everything and open it again. Sorry about that. All right. All right, we're back in business. All right, now let's move on to nitration. And nitration is where you take a benzene ring, react it with nitric and sulfuric acid, and you replace one of the hydrogens with a nitro group. Now, how does that happen? What I'm about to show you, you do not have to know for a test. This is optional, but it'll help you. Now, these are both very strong acids. And think of the sulfuric acid as a proton donor, and I'll just write it as H+. Again, this will never be on a test, but it'll help you understand what's going on. Now, nitric acid, I'll write like that. 3 oxygens, nitrogen, a hydrogen. Now, this H+ is attracted to the oxygen. And this you don't isolate. We look at what I just wrote, this new intermediate, and brackets means you can't isolate it, but we were able to prove it exists. Does anybody see something interesting in this molecule? 2 hydrogens and an oxygen. 2 hydrogens and an oxygen. Hold on, I'm thirsty. I gotta need some water. Oh, wait. 2 hydrogens and oxygen, water. Whenever you form a good leaving group in a molecule, and water is a very stable molecule to leave, it says, guess what? I'm out of here. And this minus H2O, you lose, this is water, and what's left behind? And this is called the nitronium ion. And notice it has a plus charge on it. And this is electrophile. I'm not happy, I want some electrons. And where can it find the electrons? In the pi cloud. And that replaces it, and you get back this H+, and you also make water, but those are inorganic, and I don't care about those. And therefore, the only question I can ask you on a test would be this. Unfortunately, we're not going to do this, but if we were face to face, you actually get to do a similar reaction, put a nitro group on a benzene ring. It's quite dangerous, but it's a lot of fun. It's a lot of stress for Dr. White to make sure all the students do it safely. Now, what's the general reaction? This. And what do you get? Put an NO2 group. Now, watch closely. Common mistake on test number 1, and this will be on test number 1 a week from this Wednesday. Students do this. They see the 3 there and put the 3 there. If you do that, I marked the whole thing wrong. A nitro group is NO2. This is nitration. And this is how you put a nitro group on it. And do not try this at home, and don't try and put a nitro group on toluene. You'll probably end up blowing yourself up. I would never do that. So that's nitration. Now, the next one is sulfonation. And that's where you react sulfur trioxide with sulfuric acid And similar how the H plus from the sulfuric acid reacts to form an electrophile, and that electrophile is a sulfur, 3 oxygens, 1 hydrogen. And don't put SO3, I'll mark it wrong. Don't forget the hydrogen. Now, since I'm not teaching you directors for sulfonation, this is the only reaction I can give you. So I could ask you down here, give the organic product or product, and the answer is sulfonation. And I'll put on the sulfonic acid group. Don't forget the double bonds in the ring, and it's SO3, and don't forget the H there. And that's it. Now, if we didn't have this reaction, you wouldn't have any laundry detergent the way we know it. You use, I personally like all. I've been using it for decades. Tide is good and other ones. Now, years ago, they used to help make laundry detergent work better and other molecules that were in your detergent, they had phosphates. And those were destroying our rivers and our lakes. And the government came out with, back in the mid 1970s, you've got 2 years, people like Procter and Gamble and other companies that made laundry detergent, to get the phosphates out of your laundry detergent. It's killing fish in our rivers and lakes and killing them, and also the ecosystem. And I worked one summer at the Illinois Technology Research Institute. Why it was an interesting place, was they're also at the same time doing biological and chemical warfare for the US government. But the government's, they got a project to develop phosphate-free detergents, which we did. I was doing testing and stuff like that. And the government used our data to show the detergent companies, look, it can be done, now do it. And luckily they did. How many of you have ever heard of the toxic algae bloom that happens some cities, where all of a sudden, like right off their coastline or in the river, you have this big bloom of toxic algae, which is quite dangerous. And that's from the runoff from farmland with phosphorus, phosphates from fertilizer. All right, so this is sulfonation. This is the only reaction I'll be able to ask you on a test. Hint, know it. All right, now let's go to a really interesting reaction. And by the way, these 4 reactions, the switch was on. If I could turn it up to, it only went up to 10. These 3, and this is number 4 reaction. I've turned it up to 15 or 20. Yes, they'll be on the test. Now, for many eons, and the last couple of years, it's died off a little. If you invented something very special and important, a reaction, it was named after you. And I will never ask what's the type of reaction for so-and-so's name, but this way we honor their great work. And this reaction is called Friedel Crafts alkylation. 2 chemists, Friedels and Crafts, came up with this, and alkylation put an R group on it. Now here's the general reaction. R means anything with carbon and hydrogen in it. X for this reaction is chlorine or bromine. You need aluminum trihalide catalyst, and what you do is put an R group on a benzene ring. Now listen carefully. In all of organic chemistry, it's very, very rare and very special to make a carbon-carbon single bond. It's very hard. I think I personally only know about, of the hundreds of general reactions, I'm only going to teach you about 53 in this class. Somebody counted them once. I'm only going to teach you 53. I know a couple hundred. There's only about 15, 20 reactions that I can make a carbon-carbon single bond. Something very special, very rare, and Friedel Crafts alkylation is one of them. We'll learn a couple other during the semester because they are very important. Now let's look at Friedel Crafts alkylation. And you can do this with other aromatic compounds, but I'm just going to use benzene because I'm not teaching you directors. Now, in real life, X is just chlorine and bromine, more likely chlorine, because of cost considerations. Now, R carbons, halogen, the bond, the carbon with the halogen is the carbon bonded in the R group to the benzene ring. Again, substitution, you replace one of the hydrogens with an R group, and that's called an alkyl group, and that's why it is called alkylation. Now, let me show you. And if the R group is too large, I'll put it over here to go above the arrow. I could, but and the question would be, give the organic product or products, get some inorganic stuff like HCl. We don't count that. All right, so if we look at this reaction, what do we have? Ooh, we've got a benzene ring. Remember, look for what's different, what's not a carbon-carbon single bond or carbon-hydrogen atom should get your attention like that. Now, if we look at this molecule right here, carbon-carbon, ooh, halogen on a carbon, carbon's here. This right here is my R group. This is my halogen. And I have a catalyst, aluminum trichloride, in this case, aluminum trihalide. Remember, X can be chlorine or bromine. And what happens? The carbon with the halogen is now going to be bonded to the benzene ring. So first of all, from this reaction, what you'll get is a benzene ring. What's my R group? 3 carbons. Notice the center carbon has the halogen. Do you break carbon-carbon single bonds? No. So my R group is going to be to the center because that's where the halogen was, and you have 3 carbons. And you know there are 4 bonds to carbon, so I can put in my hydrogens. And we've just made isopropyl benzene. Now, this reaction, putting on more complex R groups, also is a key reaction there was at the end of World War II to help develop detergents. I don't know if I mentioned this, and we'll see it throughout the semester. World War II, because of the limitation, the United States and England, the Allies, had in getting their hands on certain chemicals, meant they had to turn to organic chemists to come up with new ways of making molecules that they couldn't get from the traditional ways, because the enemies of the Americans and British wouldn't let us get our hands on it. Later on, one of those was we couldn't get silk for parachutes, so they came up with a compound. Are you ready for this? Coming attraction, but you got to wait a while. Nylon. And that was used in World War II for our paratroopers to help defeat the Axis countries of World War II. So let me have you try one. And there's one for you to try. What would be the organic product or products for the following? And the votes are coming in. Is that working for you when I send out a poll like that? If that's helpful, give me a thumbs up. I see a lot of thumbs up. Thank you. All right. If we were face to face, I could look in the class and see how many people are done. And also, I've mentioned this before, when we're face to face, I'll also tell the students when you're done, look up and smile. And you see some happy faces in my class, which is a good thing. All right, let's get this done. What do we have that's different? A benzene ring. What's different here? Remember, it's not a carbon-carbon single bond or carbon or hydrogen should get your attention like that. Ooh, look up here. Carbons with a halogen. And we call that Rx, an aluminum trihalide. Number X can be chlorine or bromine. And you replace one of the hydrogens with the alkyl group R, and you do something very special. You make a carbon-carbon single bond. Now here my R group is methyl, so I'm gonna have my benzene ring. Remember, put the lines or a circle, and I've made toluene. Now this is probably the most expensive way to make toluene, but I wanted to start out with something easy. Oh, let's have some fun and do something else. Have another one. Now, again, I won't be having anything on the benzene ring. We'll always start with benzene. And there's another one for you to enjoy. Have fun. And after class today, I get to put my garbage out in front by my driveway because tomorrow is garbage day. How fun, how much fun can you have in a day? But it's good to get the garbage out of the house or out of my garbage cans. And remember, I try and give everybody time to finish. Finish? No. All right, I think everybody's done. Let's get to work. Now, if I look at this reaction, what's different? Ooh, I've got a benzene ring. What am I reacting at? Carbon, hydrogen, carbon, hydrogen, carbon. Ooh, a halogen on a carbon. That's something different. And we call that Rx, where this is my R group. And we're reacting with aluminum trihalide. Remember, X here can be chlorine or bromine. I've never seen it for anything else, even though this is one area. I've worked with benzene, my last patent, I've reacted with it, but some of these I really have never done industrially, nitration or sulfonation or Friedel Crafts alkylation. All right, so you make that something special, very rare, carbon-carbon single bond. And the bond from my R group to my benzene ring goes to the carbon in the R group that's the halogen bonded to. So for this reaction now, let me move it up here where I have more room. I have my benzene ring. What's my R group? 4 carbons. Which carbon has the halogen? The end one. So I have 1, 2, 3, 4. Do you break carbon-carbon single bonds? No. And I know there's 4 bonds to carbon, so I can draw on the hydrogen. I've just made N-butyl benzene. And you can have an R group with 20 carbons or whatever. It's the same thing. You make a carbon-carbon single bond. Now, on test number 1, there'll be one reaction where you have to do the starting material. And why don't you have fun with this one? What would be the 2 starting materials you would start with to make that molecule? That'd probably be a 4-point or maybe even 6 points. Yeah, 6 points might even be nice. Or 4 points for this one problem alone. Remember, test number 1 will only have one type of problem like this, and it could be for any of the general reactions that I taught you. By the way, this is the real fun part of organic chemistry, but I'm biased because I'm a synthetic organic chemist. And now you're doing some very high level organic chemistry. Doesn't that feel good? All right, looks like most of you are done. So I'm almost out of time. So let's take a look at what we're trying to make. What's different? I've got a benzene ring, but there's something on it. And that's this right here, an ethyl group, which I'll call R. I'm reacting with aluminum trihalide. Remember, X can be chlorine or bromine. And what do you start with? Benzene. Oh, that's an awful looking benzene ring. Let's fix it up. That happens on a whiteboard in a classroom too. Plus alkyl halide. So one of these question marks up here is the benzene ring. What's my R group? 2 carbons. In this case, doesn't matter which one I put. What's my halogen, chlorine? And this will definitely make that. And that's how you do it. If I look at the clock, oi, we're out of time. Time flies when you're having fun with benzene rings and Dr. White. Now, let me remind you, on Wednesday, I will be going through the alkenes, double bond, alkynes, triple bond problem set. I highly recommend you do them first. Don't forget on Wednesday, the lab we did last week is due. Also, don't forget, coming up before test number 1, you need to upload the signature sheet. And finally, Wednesday, probably the beginning of the class, I will teach, even though I'm going to cut it out of the video. If you can't make it to class, you can come to my office hour or set up a special appointment. We'll work out something where I'll teach you how to eliminate, and I'll teach you on Wednesday, how to eliminate test anxiety, and it works well. And last thing, don't forget today from 5 to 6:15, I'll have my office hour. And with that, I'm sorry, I went a whole 60 seconds over the end of class. With that, I'll say, gehen gesund, meaning be healthy in Yiddish, or go in health, really. Yiddish, gehen gesund. Bye now. And I stole that from Beverly Hillbillies Granny.
Bye, thank you.